As a nozzle converges, does the flow velocity always increase? What are the actual limits? Subsonic, sonic, or is supersonic flow possible? In engineering, we typically categorize nozzles and flow speeds separately. On the hardware side, we have convergent, convergent-divergent, and variable geometry nozzles. On the flow side, we distinguish between subsonic, sonic, and supersonic regimes. However, these aren't isolated classifications. Instead, they represent a fundamental interplay between geometry and velocity. In this video, we're going to focus on the simplest and most fundamental scenario: velocity changes within a convergent nozzle. So, inside a convergent nozzle, does the gas accelerate or decelerate? And what is the ultimate speed limit it can reach? To answer this, we first need to grasp three key concepts. 1. The physics of flow approaching the speed of sound. 2. How information propagates through a fluid. 3. And a crucial phenomenon known as choked flow, or choking. Once we clear these up, the velocity limit of a convergent nozzle will become crystal clear. First, let's look at the physical laws governing fluid behavior as it approaches the speed of sound. Before we dive into near-sonic flow, we often start with a very familiar theory, Bernoulli's principle. You can think of Bernoulli's equation as a result of the Navier-Stokes equations under extremely simplified conditions. It is the fundamental tool we use to understand the relationship between velocity and pressure. However, this relationship relies on a crucial assumption. The fluid must be incompressible, or at least changes in density must be negligible. This assumption holds true at low velocities, which is why Bernoulli's principle is so effective for analyzing low-speed flows. But in engineering, the more practical question is, within what velocity range does Bernoulli's principle actually remain reliable? To answer this, we can use a basic compressible model to compare the incompressible approximation against the actual compressible results, and observe how this discrepancy grows with the Mach number. By doing this, we move beyond simply stating that Bernoulli fails. Instead, we pinpoint exactly when the error becomes non-negligible. As the flow speed approaches the speed of sound, this error amplifies rapidly. In near-sonic nozzle flow, the fluid becomes distinctly compressible. Velocity, temperature, pressure, and density all change continuously along the nozzle's geometry. Under these conditions, the assumption of constant density collapses, rendering Bernoulli's principle inapplicable. So, what physical laws should we use to describe these changes near the speed of sound? The answer isn't to introduce some brand new empirical formula. Instead, we return to a more general relationship with fewer assumptions, the conservation of energy. For a one-dimensional, steady, and adiabatic nozzle flow, the true conserved quantity is not mechanical energy, but total enthalpy. This relationship reveals that the acceleration process within a nozzle is fundamentally a conversion of internal energy into kinetic energy. It is from this relationship that temperature variation, changes in the speed of sound, and compressibility become non-negligible factors. And once the speed of sound becomes the critical reference scale, two questions determine the nozzle's ultimate speed limit. How does information propagate through the flow? And can the flow still be regulated by downstream conditions? This mechanism is the precise physical root of the choked flow phenomenon. Now, let's talk about sound and the propagation of information. We have seen that near-sonic flow is inherently a compressible flow problem, and once a fluid is compressible, we face an unavoidable question: how are disturbances within the flow transmitted spatially? Here, information is not some abstract concept. In fluid dynamics, it refers to very concrete physical shifts, minute changes in pressure, tiny fluctuations in density, and slight disturbances in velocity. For instance, when the pressure at the nozzle exit changes. If the flow is to respond at all, these changes must effectively propagate to the rest of the flow field. In a gas, these minute pressure and density disturbances do not propagate instantaneously across the flow field. They travel through only one mechanism: sound waves. In other words, sound is not just some extra phenomenon or side effect in nozzle flow, it is the actual physical carrier of information within a compressible fluid. In subsonic flow, the fluid velocity v is lower than the speed of sound alpha. As the velocity within the nozzle continues to increase, the fluid begins to catch up with the sound waves. For information attempting to travel upstream, its effective propagation speed is a -v. When v is small, this difference is large, allowing the flow field to adjust rapidly. But as v approaches a, the term a minus v diminishes, and information transfer becomes increasingly sluggish. The system is gradually losing its ability to respond to downstream changes. This means that in near-sonic flow, even if conditions at the nozzle exit change, the upstream response is merely delayed or even rendered impossible. At this stage, the flow's behavior is no longer determined by the nozzle as a whole. Instead, it begins to be constrained by local conditions. This marks a critical physical turning point. As the velocity increases further, reaching the speed of sound at a specific cross-section, sound waves can no longer propagate upstream at all. Physically, the downstream conditions are effectively cut off from the upstream flow. It is from this precise moment that choked flow becomes an inevitable result. Now we arrive at the ultimate limit of a convergent nozzle. In the previous section, we saw that as flow velocity approaches the speed of sound, the flow's capacity to adjust to downstream changes diminishes rapidly. Now, let's do just one thing: return to the absolute simplest geometry, the convergent nozzle. Let's see exactly where the flow ends up under these information-constrained conditions. Let's start with subsonic flow. In a convergent nozzle, the cross-sectional area decreases along the flow direction. For subsonic flow, this is the key rule. Reducing the area forces the velocity to increase. As long as the flow remains subsonic, sound waves can still propagate upstream. This means changes in downstream pressure can effectively influence the entire flow field. At this stage, if we gradually lower the back pressure at the exit, the flow field adjusts continuously and the velocity keeps rising. From an engineering perspective, this is a smooth, controllable process. We can verify this process using a very simple computational model. By fixing the nozzle geometry and the total inlet conditions, we use Python to sweep through different exit back pressures to calculate the resulting velocity and mass flow rate. In the subsonic range, you will observe a very intuitive result. The lower the back pressure, the higher the mass flow rate and velocity. The model shows no discontinuities or sudden jumps. Everything remains perfectly continuous. However, as we continue to decrease the back pressure, the flow velocity at a certain point begins to approach the speed of sound. In a convergent nozzle, this specific condition can occur at only one location: the minimum cross-sectional area, also known as the throat. In the subsonic regime, the term m²-1 is negative. Consequently, a decrease in area leads to an increase in velocity. However, as we approach the speed of sound, a mathematical constraint kicks in. For the velocity to continue changing, the change in area must approach zero. In other words, sonic velocity can only occur at an extremum of the cross-sectional area. Conversely, if the flow reaches the speed of sound, the area gradient must be flat. Therefore, in a convergent nozzle, if sonic speed is achieved at all, it must be at the point of minimum area, the nozzle exit. If we continue the Python sweep and plot mass flow rate against back pressure, we see a distinctive pattern. Beyond a certain threshold, the curve plateaus. No matter how much you lower the back pressure, the mass flow simply refuses to increase. This limit isn't artificial, it is a result of physical constraints. This is choked flow. Crucially, choked does not mean the flow is blocked or stopped. On the contrary, the flow at the throat is sonic. and mass flow is at its maximum. What has actually changed is that downstream conditions can no longer regulate the upstream flow. In engineering terms, once choked, the mass flow depends solely on inlet conditions and the throat area, independent of the exit back pressure. But what if the incoming flow is already supersonic? In this regime, sound waves are swept entirely downstream. This means, right from the start, downstream conditions have zero influence on the upstream flow. In a convergent nozzle, such a flow is fundamentally incompatible. Instead of accelerating, the converging geometry forces the supersonic flow to decelerate. In reality, this deceleration is often accomplished through a shock wave which forcibly converts the flow back to a subsonic state. From an engineering standpoint, a convergent nozzle is simply not the right structure to handle supersonic flow. This reality becomes crystal clear in our numerical model. When we attempt to force a steady supersonic solution inside a convergent nozzle, the model reacts in one of two ways. It either fails to converge, or it automatically snaps back to the subsonic branch. This isn't a numerical glitch or artifact. It happens because such a steady-state solution simply does not exist in physics. So, Python's role here isn't to generate an error or a wrong result. Instead, it acts as a tool to help us distinguish between what is mathematically possible and what is physically untenable. Putting all these pieces together, the velocity behavior within a convergent nozzle becomes crystal clear. Subsonic flow can be accelerated continuously, but its maximum speed is capped at the speed of sound. Once that speed is reached, the flow becomes choked, and supersonic flow simply cannot exist stably within this geometry. Ultimately, sonic speed isn't just a design target. It is an insurmountable limit dictated by physical constraints. But what if, in engineering, we do require supersonic speeds? The answer isn't to constrict further. Instead, once the speed of sound is reached, we must give the flow room to expand. Join us in the next video, where we'll discover why supersonic nozzles must be convergent-divergent and exactly how variable geometry nozzles work.